Thanks everyone for joining our Engineering Tomorrow session today. We're going to focus on a biomedical engineering application using phototherapy. And it's an exercise that we'll be starting in a few minutes. But first, I'd like to talk about engineering as a field of study. I'm thrilled to have been an engineer and still have the engineering tendencies. I didn't spend the vast majority of my career in engineering. I started out with an engineering job, and then I moved into management. But I will tell you this, the engineering skills, problem-solving ability, and analytics have helped me in every single job, and I think it's given me a competitive advantage. I'll spend a few minutes to talk a little bit about my background. I first started as an engineer for the Lindy division of Union Carbide. I was a process engineer, and I worked on a unique technology at the time, but very popular today, and that is waste to energy. I was working on a number of aspects of developing that process, and we actually built a prototype plant in Charleston, West Virginia, processed 200 tons per day of municipal waste. And over time, as we debugged all the things that were failing to operate and added filters and cleanup systems and shredding and pelletizing operations, the cost of the project got out of whack. And I learned a lot about the importance of engineers understanding economics and cost. I moved from that assignment to another division of Union Carbide located in Houston, Texas, where I worked on the application of industrial gases to decoke fired heaters. These are huge heat exchangers used in petrochemical refining and chemical operations. And the whole idea was to improve the life of the furnace tubes, or the metal that was carrying the fluids through the furnace, through the heater, and also to improve the thermal efficiency and to use less energy. That's where I got my first patent on a breakthrough technology to do an even better job in operating these furnaces and in removing coke or deposits. After that assignment, I moved to a consulting firm, and I started getting more involved in management of large organizations. I worked for a firm called McKinsey & Company. It was a management consulting firm. I was in the Houston office, spent a lot of time in Dallas as well. And most of the work was in transportation and in energy. Spent a lot of time in refineries and plants throughout the Gulf Coast. There again, having an engineering background was really important and helped me tremendously to be successful in that firm. I stayed there for about 4 years, started a family, and didn't like all the constant travel, so I started thinking about what else I might do, and I got a call from General Electric, GE, to go to work in one of their divisions, the lighting division, as head of strategic planning. I spent 23 years at GE in various jobs. Some of them were in materials and chemical businesses. Some of the years were in GE lighting. I also worked in GE Capital for about 2 years. And then I became the CEO and president of GE Specialty Materials and then GE Infrastructure. I left GE about 17 years ago and started a new company called Global Infrastructure Partners. It was a company designed to acquire, purchase, and operate infrastructure assets around the world. And the categories we invested in were in transportation. We owned and operated 3 airports in the UK. We also have Sydney Airport in Australia right now that's in our portfolio. We also operated train systems, a high-speed rail system in Italy, and a big freight train rail system in Australia. In addition to transportation, and our biggest segment that we operate in is energy. We were very instrumental in getting invested in renewable energy in the United States, then moved to other parts of the world. We're one of the largest producers of renewable energy in Asia. That includes solar as well as wind and some battery storage. And we're, I think, the 4th or 3rd largest producer of renewable energy in the United States with a company called Clearway. So that's been a big emphasis of our business. We've also invested in liquefied natural gas. Some of these facilities are so large that you can actually walk through the pipelines that carry the gas into these facilities and then liquefy using cryogenics. Fascinating technology and a great way of getting low carbon intensity gas, less pollution than fuel oil, and gas will be a vital part of the energy transition. So we see that business as thriving. We also do investments in a number of different pipelines that are carrying both natural gas and crude oil and refined products. Engineering has been a big part of my work at Global Infrastructure Partners. We've spent a lot of time using industrial engineering tools to optimize the way we run our assets. And it's been a huge part of our success and has allowed me to build a team of about 30 plus engineers with varying skills from process engineering, chemical engineering, to mechanical, to industrial, as well as some of the other disciplines like electrical. I have 2 engineering degrees. The first, my undergraduate degree, is from the United States Merchant Marine Academy, and the second is a master's degree from Northwestern University in Evanston, Illinois. I grew up in Queens, New York. I was in a lower income family. I had 2 wonderful parents, but we didn't have much money. So I chose the Merchant Marine Academy because it was free. It was a federal program like West Point or the Naval Academy. And I was able to study marine or mechanical engineering there. At Northwestern, I studied a hybrid degree, mostly chemical engineering, some environmental. And after those 2 programs, I felt I had a really good practical education from the Merchant Marine Academy and a really good understanding of chemistry and chemical processing technology from Northwestern, more theoretical program. So what I'd like to do now is talk a little bit about Engineering Tomorrow. I'm the founder of Engineering Tomorrow, and I felt with the success that I've enjoyed in life and in business, I'd like to give back. So the whole idea in my mind at the time I was thinking about how to give back was reflecting on my teenage years, high school years, where I didn't have a mentor. No one in my family went to college. There were no engineers. I didn't know an engineer. And I was sort of fortunate in going to the Merchant Marine Academy and picking engineering, but I didn't do it with a lot of insight and a lot of information. So I always felt that was an aspect of giving back that might make sense. The other thing I felt when I was in high school is I didn't see how math and science was practically used. I didn't see how those fundamentals were applied to engineering or the real world of having a job. So I thought if we could do something to help inner city kids, less privileged kids, to see a path in engineering, and for us to connect the dots on how math and science is used in engineering, and the math and science you learned in high school and are learning in high school, that would help create opportunities for people to knowingly pick engineering as a field of study. So as a basis, today I'm going to share a class that is a true story. I suffer from a skin disorder, we'll talk about it more in a second, that had no cure. I worked on several options to try and find a cure, and ultimately had to do something that was more difficult than just taking a pill or taking some kind of cream or lotion. So this is a true story. You're going to hear how an engineer that's not trained in biomedicine or mechanical engineering, and you're going to learn how I approach the problem, and then we're going to all do a lab exercise that will reinforce the approach to the problem. So I'll start with my first slide, which is engineers have the right focus. Here's what an engineer has that I think is extremely beneficial to problem solving. And in my case, solving a problem where the dermatologist had no idea how to cure it. We're fact and data driven. The data to an engineer is the foundation of everything. We like numbers, we like analytics, we like metrics. It allows us to establish a baseline and to establish an approach to improve. Engineers have good process skills, and what that means is we think in sequences. We don't just think in one particular realm. We'll move from the beginning of a process to the middle to the end very methodically, not skipping any steps. We also have the mentality to find what is the root cause of the problem? What's the basic foundation of why the problem exists? We are very detail-oriented, and we tend to have a very executive or economic focus in how we think. The beauty of engineering is it combines math, science with economics. We have to produce products that are economically viable. We have to work on processes and business performance to make it even more economically viable. So these factors are critical in the skill set that you gain as an engineer. So let's get back to the actual lab exercise and the biomechanical, biomedical aspects of this study that we'll go through. I have a skin condition called Grover's disease. It's transient, meaning that it comes in the wintertime in the northern hemisphere and goes away in the summer. Most people with the conditions are male and over 40 years of age, and the disease recedes at its own pace, but I will tell you it is extremely itchy, and you can almost see the itch in this photograph. It's also unsightly. There's no known cause, and there's no effective treatment. Dermatologists have not been able to determine how to deal with this skin condition. So an engineer's approach is listed on page 4, where identifying the problem is critical, brainstorming possible solutions, selecting one, testing its effectiveness, and then optimizing around it. That's the process that most engineers go through, whether it's designing a new product, solving an issue with a disease, or optimizing the way a business is running. So as I was assessing how to approach solving this problem, I had two possible solutions in mind. One was the use of steroid creams and antihistamines and beefing that up and working with dermatologists on trying different treatment systems. The rash persisted and the itch would go away for a couple hours and then it would be back. And as I mentioned, the itch was intense and in fact got to the point where I couldn't sleep very effectively. So then the second approach was to connect the fact that I saw this disease come in the winter and go away in the late spring. And I thought it had something to do with sunlight. And perhaps it was sunlight and the synthesis of vitamin D in the skin from the stimulation of sun. So I took vast quantities of vitamin D3 over time, and I had my doctor, an internist, monitor my blood levels. And I took the D3 levels up to 7 times normal, and I saw no change in the rash, and I didn't see any reduction in the itchiness. So now I was back to the drawing board, but I had in my mind it had to do something with light because it goes away when I'm outside more often. I like to play golf. I like to go sailing. I thought there was a connection. I stumbled upon some research material as I was teaching myself about light and skin and the body from articles in the medical journals. And there was an article from Georgetown University that was very impressive to me. It talked about how the immune system in the body appears to improve with the exposure to the blue wavelength of light. It's 450 nanometers. It's the measurement of the wavelength of the blue light in the natural spectrum of light. There's an immune system in the body called T cells. And T cells are just like white blood cells, only white blood cells are derived from bone marrow, and they're called B cells technically. And T cells are derived from the thymus gland, which is near the heart of your body, and it's about the size of a deck of cards. As you get older, that thymus gland starts to lose its effectiveness, and that's why I felt maybe the disease affects people older than age 40. So it was a theory, and I started to think, could it be that the deficiency in sun affects my immune system, lowering it, And maybe the lower immune system allows this Grover's disease, which might be residual in my skin, to come back and to manifest itself in those blotchy, itchy, scaly pimples. So I started thinking about light. And you learn about light in physics in high school, and you learn about it when you take physics again in college. But light is made up of a number of different wavelengths. And you can see ultraviolet at the bottom right, all the way up to the visible light spectrum at the top. One might say, when do you see light in these color patterns? And so think for a minute, when do you see light in these color patterns? Normally it's after a rain in the summer or warmer weather, where then the rain dissipates and the sun comes out and you see a rainbow. Well, the colors you see in a rainbow are the spectrum of different wavelength, and some appear blank to the eye, in other words, invisible, and some are visible. Blue light is at the bottom of the visible chain, and one thing to be observant of, it doesn't include any ultraviolet. And the concern about ultraviolet is the skin cancering aspects of using UV light. So I had that in my mind. One of the things I was thinking about with sunlight activating the blood T cells is how can we measure the activation? And fortunately, this research talked about the fact that the T cells move 200 times faster. They actually can swim against the flow of blood in your veins and arteries. And the immune system can jump 7 to 8-fold. So I thought, I'm onto something, because this is probably the reason why the rash comes in the wintertime. And I thought, can we study and test blue light to trigger an improved immune system response and treat this disease? So then the question becomes, how do you do that? So that's really the challenge of this phototherapy lab exercise. And I'll walk you through a little bit more about how to approach this analysis by starting with designing a solution. You can calculate the irradiance of the sun and how much you absorb over time. So I live in Connecticut, and I thought the rash goes away when I start to play golf. So I figured, okay, let's think about 5 hours of being in the summer sun, early June. And let's think about the fact that I'll have a shirt on. I'll be in a golf cart sometimes. I'll be walking under trees. So there's some factors here where it's not fully in the sun. And you can get from the internet sun's irradiance levels for any particular area of the world in any particular time. So I was able to get the sun's irradiance for June 15th, middle of June. I was able to determine the area of exposure on the body, the surface area of the body. You can do that through, there's formulas in the internet on how to calculate it, and there's also some other techniques that you can use to figure that out. And then the duration of exposure would be used to determine how much irradiance have I absorbed. You're really getting at how much photon energy have I absorbed by being in the sun. There's a couple of factors, though, that you have to think about. First is blue light accounts for only 8% roughly, actually 7.8% of all natural light. So you could take the irradiance level of 10,600 watt hours and multiply it by 7.8%. And that reduces the amount of actual absorption to 825 watt hours. But also, you have clothes on. You have a hat. You have a golf cart. You have shade, trees. Angle of light is not perfect. And cloud coverage from time to time. So let's estimate, and this is a number I used, that about 5% of the sun's light is truly absorbed. So of the 825 watt hours of blue light energy in the sunlight, 5% of it is what actually was entering or touching my body. So that's 41 watt hours of irradiance, and that's actually the goal for us to drive towards. So thinking about how to design a solution, how do we replicate the sun's ability to supercharge the T cells, knowing what we know? And the thing we have to think about are the variables that will allow us to do this and allow us to change parameters as we see fit. economically fit, as well as the time you can stay in a doctor's office. You don't want to be in a doctor's office for 4 hours. If you could do it in 20 minutes, that's doable. So you have to look at wattage of the light source. You have to look at the distance from the light source, and you have to think about how much time you spend from the light source. The task for you in this lab is to use the blue light flashlights and photochromic paper that allows you to determine the light energy coming off in the blue spectrum. So you and your team will first measure the blue light irradiance 3 times, holding the light at different distances from the paper, the photochromatic paper. And practically speaking, it's best if you choose distances between 2 and 10 inches. That's sort of a practical range. And then you'll measure the area of irradiance for each of these distances. So what surface area at those distances are you touching? Keeping in mind the fact that the goal is to have 41 watt hours of exposure. And then you need to determine the treatment time, the residence time you're in front of the lights. This is critical. And as I mentioned earlier, you don't want to be in a doctor's office for 4 hours. If you could do it in 25 minutes or less, that would be an ideal time. So, continuing on the process step of designing a solution, we're going to expose the paper from the blue light in your lamp for 10 seconds, and then match the shade of red on the scale, almost like a pH measurement in high school chemistry. And you're going to be able to record the values 3 different times. One word of caution, don't shine the blue light in your eyes or anybody's eyes in the experiment, because blue light can damage the retina. It actually can burn the retina in the eye. So you're going to measure at different distances what the irradiation level is and map it to the template on the photochromatic paper. You're also going to measure the surface area at different distances the light is held from the surface of the body. So you'll use a ruler and measure the radius of the circle created by your flashlight. And as you move the light further away, the circle will get bigger. And you'll use the equation for the surface area of a circle, pi r squared, and you'll divide this by 10,000 to convert your area to meters squared. So you'll measure your area using the radius in centimeters and divide by 10,000 to convert to square meters. And as your distance increases, in other words, you move further from the body, the area will widen. And that's important as you start to think about how many light sources will I need to cover as much of the body as possible. But as you would guess, as you move further away, the intensity of the light drops off. So if you look at the area of absorption, it's very high on the far left. And if you look at the average irradiance, it's very high on the far right. So you have to find the sweet spot of where do you get the right mix of surface area coverage and irradiation level. The next step gets to that very point. On the cutout figure, you'll use different color paper to cut circles the size of each of the areas you've measured earlier. You'll then place, on the 3 measurements, you'll then place the circles around the cutout figure and decide what's the right configuration. And then you're going to multiply by 2 to account for the fact that you have to do front and back. The next step is really critical, and that is to determine your treatment time. So we're going to take a formula that we touched on the earlier slide. We'll take the sun's irradiance level times the area of exposure times the time of exposure, and that will give us the watt hours of energy that we've absorbed. To get the duration of exposure, you're going to run this equation to solve for duration rather than irradiance absorption. And when you do that, you'll be able to do this following calculation. You'll be able to figure out how many lights you need, and using a cost of $50 per light, you can calculate the total cost of the device. Once you have that, you begin to have the first step of understanding the economics of the time of exposure with the number of lights. Now I'd like to show you the actual device that I designed, and I'm going to turn it on, and you can see the power of the blue light that's being generated, and get a sense of what the device looks like. You'll see it's probably more complicated than just a simple light bulb that perhaps you were thinking, and it has a lot more engineering involved with it, but I think you'll enjoy seeing it. Now I'm going to demonstrate the actual blue light that I used in my experiments. I'm going to put on these goggles when I turn it on, because recall in our discussions that the blue light can burn the retina of the eye. So I'm going to be careful not to go with the naked eye. And what I'm going to show you is the light source as it relates to the cooling fins and the LED diodes. And I'll briefly describe the drivers, and we'll get into then actually flipping the light on. A funny story to share is when I first flipped this light on, I was in a different house, and the kitchen door had a gap separate from the floor of the kitchen. And when I flipped the light on, I could hear my wife and the dog scurrying around, and she yelled to me, "There's blue light coming from under the door, filling the kitchen with blue light." And it was freaking the dogs out. So these things are powerful. LEDs generate a lot of energy. There's a lot of photons being emitted by this light source. And think about it. 20 minutes in front of this light source is equal to 5 hours of sun in Connecticut in the month of June. So it gives you a sense of the amount of radiation, or radiance, I should say, coming out of this light source. So let me get started. I'm going to put the light on and switch to my goggles, and I'm going to point out some things after I turn the light on. Okay, the lights are on. I'm going to put on my goggles. You may not be able to see it with the concentration of blue light as high as it is, and I'll turn it off in a second. But there's two 28-inch batons of LEDs. Each baton is roughly 200 watts. And LEDs are extremely efficient, so the amount of heat they're generating is far less than an incandescent bulb. Right now, you may not be able to see it, and I'll turn the light off in a second to show you there's cooling fins. And that's because even with the efficiency of LEDs, in other words, all the energy is being put into useful light, there's still some heat loss. And the purpose of the cooling fins is to keep the light from overheating. So this is in warm-up mode. I'm not going to leave it on much longer, but it starts to give enough irradiance that I can feel the heat this far away, and I can still feel it this far away. So I'm about a foot away, and it's still generating a fair bit of heat. So now I'm going to flip it off and show you the design of the unit. These are the cooling fins that I mentioned. They run down the length of the light source. You can't see it on the camera, but there's another one of these batons below this. So when you stand in front of it, you're getting irradiance from the lower 200 watts of energy for the lower part of the body. Let me call it waist down. And the waist up, you're getting irradiance from the second baton. So you're getting the equivalent of 400 watts. And these heat exchanger fins are designed to keep the surface of the LED cooler and to not cause any fires. So that's the system. Took a while to design it. The key was to use fundamentals of math and science and physics to figure out irradiance, matching it, what wattage we needed for the LED source, how to establish it in a format that would give good coverage to the body. Some additional thoughts. So as an engineer, think about what other measurements and what other knowledge would you need to have to further develop the device. Well, one of the things I thought of is what happens with different fabric that you might wear while you're playing golf or while you're sailing? And what is the blocking ability of certain fabrics to the blue light? There's a lot of SPF 30 shirts, SPF 50 shirts that people buy to wear in the sun. I have some when I play golf. Does SPF shirts of 50 or 30, do they block blue light? What does a cotton shirt do compared to a wool shirt? So I experimented and I found the wool shirt actually blocks 90% of the blue light. A cotton shirt and an SPF 30 or an SPF 50 shirt blocks only 10%. So you start to get a sense of whether or not certain fabrics should be worn at certain times of year to improve and enhance your ability to take in blue light. The nice thing about the SPF shirt is it doesn't block blue, but it blocks UV. Another thing I spend time studying is perpendicularity. That's where you get the most absorption from a light source. So if you can lie down flat at high noon, you're going to get the most sun exposure. And as the sun shifts, you'll move your chair on the beach, you'll move your position in the sand to try and get that perpendicularity. The other thing that happens is on advanced solar energy production, the solar cells actually move on a table. They're attached to the table. The table moves to follow the sun. And as it follows the sun and moving from east to west, it's always looking for a perpendicular pattern. And that's the maximum amount of absorption that you can achieve, being 90 degrees angled perpendicular. Another question you have to ask is, how do you protect your invention? So I'm going to talk about that for a second. Patents are designed to help protect inventions and people's creative activities. In this case, when I saw the success of treating myself with this blue light and then treating a couple of friends who had Grover's disease, I decided to file a patent in both the United States, Canada, and the European Union, including the UK. And here's what a patent looks like. There's a number of things that a patent does for you. It gives you roughly 20 years life of your technology and your uniqueness, so it protects you from people who might copy you or try and introduce a product into the market that competes with your technology or your patent. A patent requires basically three things. One is a pretty thorough description of what you're doing and how you're doing it. The second is an analysis of what other products are out there that do something similar or the same thing. And then the third is probably the most important, which is what specific claims do you have on your patent that makes you solidly positioned, different than others that might be in your realm of treatment, but yours is different, more effective for a number of reasons. Those reasons are really the claims that go into a patent. So when you think about technology, you have to think about economics, you have to think about durability, quality of the product, and you have to think about how do you protect it. And that's the role of the patent. So with all this said, I think it's time that we can start the experiment. And I think it's going to be fun and exciting. And you're going to see firsthand the steps that I went through, and you'll now go through them to develop this technology and to have a point of view on what's the most cost-effective design that you can come up with to achieve this goal. Good luck, and I hope to talk to you soon. Bye.